Yeah, ladies and gentlemen, welcome to another lecture here on fundamentals of electrical stimulation. I can promise you that this one and the next lecture might be the most unpleasant ones for you because this is about electrochemistry. And electrochemistry is the topic that engineers don't like because they think this is chemistry, and the chemists don't like that because they think it's engineering. And I'll try to bring that in with a pragmatic view how we could probably describe that. I know I promised that I set up the Ilias page. We are still struggling with the conversion of those things. This is a brand new Camtasia version that takes about 40 minutes to make something readable out of that. And we have now an idea how to do that without blocking here the lecture halls for eternities. But I was still busy with a 10 million euro grant proposal the last week, so that had a little bit higher priority, to be honest. But I'll promise Friday looks good, so I'll set up everything. I put on the additional literature. I'll check it out, and then you get the actual password and link with everything. And I believe you're not that keen on already re-listening to those slides so far. Yeah, so electrochemical reactions. The plan is to give you an idea what happens here and how can we measure that, and why do things look like as they look. And this comes not only with a scientific point of view, but quite often a lot of things that happened over the last 50 years reflect a kind of the state of the art. Yeah, it started in early days with analog electronics. And people did the best what they could do with analog electronics. And nowadays we're sometimes with, how should that work? You know, if I take an A to D converter, and no, there was a switch and a capacitor, and people had to deal with that. And therefore, I'll try to make links to that you get an idea why has this been used or something like that, because in some cases it's not intuitive at all if you just see it without the historical context. I hope that I get you all on board on that. I know some of you come from engineering. They have seen Maxwell's equations more often than those of you who don't come from engineering. But I'll try to make it, let's say, as simple or as intuitive as possible. I don't say that it's trivial, but if you get a grasp on that, it's probably easier for you to find whatever online lecture that gives you some insights in the details that I could not deliver here on the master's level. And if I would start with really the very beginnings, it would be probably too boring for the other half, so I'm always trying to hover through those things. This is here what comes in the slides, and I don't want to read that. I want to start with the pulse forms. So if we do electrical stimulation, we need some stimulus pulses. And as technical devices are not a one-to-one copy of the nervous system, you can probably imagine that people did not try to record the action potential and make a template of the action potential and stimulate the action potential then into a nerve. But the idea was, let's make it as simple as possible. And what can you do as simple as possible? As you can imagine, you switch on electricity and you switch off electricity. I say electricity here on purpose because we have to agree on the type of the amplitude. So if you remember last week, the nerve cell, we had ions being inside and outside. So that sounds like charge. And if we have charge charge creates an electrical field. So we can use voltage to describe the gradient of the potential due to the plus balls and the minus balls, so the charge distribution that we have. If we now monitor the charge over time and it moves a little bit, moving charge is current. So that means we can either use voltage as driving force, or current, or charge. And due to some equations in the background, they are somehow linked to each other. But depending what we do, one is preferential over the other. And therefore, I apologize now that I might switch between them. As we'll see later on, there is a good reason to use current as one of the descriptors here, and I try to stick to that. So we have a current amplitude, and since we control that current amplitude, we'll talk about a constant current control. That does not necessarily mean that the current is always the same over time, but we exactly know what current we have over time. Yeah. So if we look here on A, upper left, and you'll see we have here English translations, and sometimes we have some German original data here. So this is, for example, a switch, and we switch it on, and then we have direct current 0, direct current on, and then whenever we like, we switch it off. Or we switch something on and off. And this is wrong, as I see. This is apologies. This is not by an inductor. This is by a capacitor. No idea why this inductor is there. So we switch on a current. First part on B. We switch off the current, and when the current passes a capacitor, the amount of charge that the current gives is stored on the capacitor. And if we have a reasonable amount of switches, we can then decharge the capacitor. And if we wait long enough, the current that goes from the capacitor is the same current that we put on the capacitor before. So we have an analog charge balance between one phase and the other phase. And you'll see later on some circuits about that. So that is the idea from analog world. Don't try to replicate this with a digital circuit. You get sleep deprived. That doesn't work, because there's processes that you can simply describe. I put the charge on a capacitor and I let it flow away, is described by exponential equations. If you combine exponential equations with a linear equation, like current I times time t, and combine that with an exponential expression, you get to an equation that looks simple, but that you cannot solve analytically. I did not believe that. I blocked my whole department in which I worked with 30 persons for a whole week. I tried that because there were very old physicists there. That means 10 years younger than I am now when I was a young PhD student. I said, no, we find a solution there. We find one. And then, you know, people were standing around their coffee mugs and were discussing, and on blackboards with chalk and on whatever. It didn't work. So at the very end, we had a numerical simulation, and when I did that in practice, I found out that the decay of that curve was described by 3 data points. So I could have taken whatever curve, because in 3 data points you cannot discriminate. Is this x to the square? Is this an exponential thing? Is this just a linear thing? So it's always good to look for adequate solutions. And I oversaw to those days that this was created by analog circuitry. And if you want to port that, if you want to put that one-to-one into digital circuitry, it doesn't make any sense. So you have to understand about the backgrounds, and then you know what you should do. And we'll find that out in one of the ongoing slides here. So it goes all back to the 19th century, where Flüger, a German physiologist, found out if I put charge at a certain time, I can excite nerves. And I should do that by changes in polarity. That is equivalent to what we've seen last week. If we have a displacement current on a nerve cell surface on an axon, then we get reversibility in charge, and then we trigger the action potential. That's the same here. And the question now is, how should I do that? How should an ideal pulse look like? And ideal is nerve excitation, simple to implement with the circuitry, the electric, and safe for the electrodes, and safe for the tissue. So we don't want corroded electrodes, because then they go away. We don't want to kill the tissue that we want to excite, and the circuitry should be small enough that I can carry it around. Yeah, and this should come together then. What we will use at the very end is something like that. That is a symmetric pulse. In many cases, we have it rectangular. That's easy to implement with both analog and digital circuitry: on, wait, off, reverse charge, on, off, and then wait for a certain period of time. And the area under the curve is the same in the positive and the negative pulse. That means we have a charge balance. We push as much charge in as we pull out. And in an ideal world, if we do that, same in, then out, nothing is left. And if nothing is left, I haven't done anything. That's, of course, not the full truth, because we have time. Yeah, and something can happen over time, and we'll see what that is. And we have to take care that we don't mess it up over time here. We always start, not always, but we quite often start with the cathodic pulse first. That means we define one spot and say if the pulse gets negative first, that's cathodic. That's the activation, and then we do the anodic part, the positive one, as charge balance. That's kind of standard. You will find non-standard things, but that's kind of standard. And if we do it without thinking too much, we will see, oops, there is an artifact. Artifact is always something from the Latin, which is done artificially, so we don't want to have that, an artifact. That's a kind of side effect. And this is called the anodic break excitation. That means if we look under the anode and we switch the anode off, then we see an activation of the nerve. Why? Try to make a sketch here. If we have excitation on the cathode, and we have a current source here that goes to the anode. Stupid but important, we always need two electrodes to close an electrical circuit. Yeah, one where the current goes in, the other where the current goes out. If somebody tells you he or she does only need one electrode, there is a mistake. Then you have to look for a hidden second electrode. There's some persons who would sell their mother saying there's only one electrode. And then if you look it up, you find the ground connection between that electrode, the charge generator, and, for example, the ground of the operation theater table, which is made out of metal. means that the circuit is closed by that. So we have to take care from the engineering side to find that second contact there and to understand where it's closed. And if we go here from 0 to something negative downwards, we find the same, so to something negative. This is the opposite way on the anode. So then it would go from 0 to something positive on the anode here, because it's just reversed. And I don't want you to go through that, because I always make mistakes here when I do that on the screen, so please do it by yourself. If you do it on the anode and you shut off the current at the anode, you find the same direction of current flowing there, which then might excite the nerve over there. The question is, can we prevent that? I don't give you an answer, but ask you for a bit patience for one of the next slides to find that out. Before we go there, we have to look on some more complex things that are sketched out here. We should agree, or you have to agree with me in this course, that we talk about the pulse width as the width of a single pulse. If we have two pulses, one after the other, then it's twice the pulse width. So the pulse width always describes one pulse here. Should be on my other computer, it was still better in resolution, should be PW for pulse width, the small t. And if we take the first edge of such a pattern and go to the same edge of the next pattern, that's called a period. And 1 over the period is the repetition frequency. Same as everywhere. If you have a repetition frequency, the inverse is the time period of that. And in between there might be differences. So there could be a delay between the cathodic and the anodic phase, and we call that D. There are some physiological reasons why it might be clever to include that. And I don't want to switch between, let's say, chemistry and physiology. So we do the chemistry today, and when it comes to the effects, later on I'll jump back to that mechanism. And as you see on the right-hand side, we might come up with pulses where one polarity is different in amplitude from the other. If we want to maintain charge balance, the area under the negative pulse and the positive pulse should be the same. And that means when I decrease the amplitude, I have to increase the pulse width. So I times t should be equal to I times t. If you do that in extreme cases, for example, fixing the second pulse at 20 microamperes or 40 microamperes, and saying, well, my first pulse should have a pulse width of 150 or 200 microseconds, which are typical numbers for those pulses. And I want to have a repetition frequency of 20 or 40 hertz, then your amplitude of the first pulse is limited by the time period. That sounds a bit strange, because when you think, well, 150 microseconds compared to 20 hertz is 50 milliseconds. But if you decrease the second pulse to very small numbers, they get extremely long. The reason for that you have that imbalance is, for example, to suppress that anodic brake excitation. You need a certain amplitude. If you stay below that threshold, it doesn't happen. One of the famous, where it took me half a year to get the word out of my mouth, is quasi-trapezoidal pulses. That is that here. With the second idea, if I don't switch off the pulse immediately, but slowly sneak to the equilibrium, I can trick out the nerve. And by that, you also can get no anodic brake excitation. What this is all good for comes later on with respect to the physiology, but just to give you an idea. That means people come up with a lot of pulses here that have then later on make physiologically sense. At the end, I've seen so many theoretical papers, and when it comes to the transition of something in a medical device, it's so hard to prove the safety of complex circuitry that a lot of people say, hey, come on, let's go back to those rectangular pulses that are much easier, and we try to handle other effects with different measures. But I think it's still worth keeping them all in mind, and then later on see how we can combine physiological sensitivity, excitability with safety from the chemical side. So one thing that goes hand in hand is the recruitment of fibers and the stimulation. If you remember how we modeled the axon last week, we had something like longitudinal resistivity with respect to the diameter of that cylinder. And we said the larger a cylinder is, the more surface we have. And the more surface we have, the more ion channels could be decorated on that. And if we know that, and we make now a nerve here composed out of small nerve fibers and large nerve fibers, and have the electrode here, that square-shaped thing with a minus for the cathodic phase, and this is now your transfer task for today. It's minus, and for a stupid reason, all those pulses are drawn in the positive direction. So it would be probably more clever to have the pulses in the negative direction if it's minus, but I was too lazy to do that by hand. I copied that just. But if you stimulate now with a given amplitude, a nerve, you will reach certain fibers, and the thicker they are, the lower the excitation threshold. The thinner they are, the higher the excitation threshold. If we look on the left-hand side, we see that the thick fibers are activated first, even thick fibers in a certain further distance, and that the very thin fibers, due to their high excitation threshold, are not yet activated, even though they are closer to the electrode as some thicker fibers in deeper layers. If we now increase the amplitude here on the right-hand side, we get the threshold of the thin fibers in superficial layers, and on top of that, we get thicker fibers at deeper layers. That is called inverse recruitment. This is something you always get in such a nerve. And that's quite stupid for many reasons. Stupid with respect to what we like to get, because physiology does it in the other way around. Yes. Yeah, physiology does it in the other way around. Because in physiology, we would say we take the thin fibers first to get the slow muscles first. Yeah, for stable things. And if we have to balance out because somebody bumps in me, then I need for a very short period of time the thick fibers, that they react very fast to get me back to balance, for example. That's now, I have to repeat that here for the ladies and gentlemen at home. The question was, isn't it just the same? Because if you have, I try to cut it a bit shorter. If you have thin fibers, nerve cells with thin fibers and nerve cells with thick fibers, that the thin fiber nerve cell need less current. Depends on the input structures. It's not that easy. If we have motor units, they might belong to different control paradigms. So they're intermingled, and let's say the motor pool for the small fibers, motor pool describes the amount of nerve cells that belong to one task, could be probably modeled by the brain, by whatever part, and some of the thick fibers are from another motor pool, which is probably first also controlled by the brain, but has another loop on the intersegmental level as a polysynaptic reflex arch. Then you would get a stretch on the whatever tendon organs, or a stretch on the other fibers that gives a hierarchical control loop on the lowest level in the spinal cord. We said, oh, increase tension. They need more ions, but they might need less input. That depends how they're connected, you know, how much, that is the strength, the intersynaptic strength, how much you need to model that. So it's not that easy. We cannot transfer that one-to-one to that excitation, because second thing, what trick is played here, we're here on the axonal level, and all those control things are mainly happen on the dendrites and the somata. That means we have a kind of input control that is completely taken out here. But you're right with the physiology. The balance is one example, where thick fibers go for fast control to keep me at stance, for example. Another thing which we will get on many aspects is control of the urinary bladder. The sphincter needs to be fast, so we have a striated muscle which is fast, which has fast thick fibers, fast conducting, and we have the bladder wall muscle, which is a smooth muscle, which is cool thing, little input over small fibers, and it contracts very long. Yeah. And unfortunately, those fibers are mixed in the sacral roots coming from the spinal cord, S2, S3. If you stimulate them, you stimulate the sphincter first, so your bladder is tightly closed, and afterwards you stimulate the bladder wall, which doesn't make that much sense, right? Because then the bladder is closed and you increase pressure. This is used in spinal cord injured persons in one application, for example. But, and that is the genius that the guy had who invented that, if you switch off the current, the sphincter has a fast release, so opens, and the bladder wall still is compressed. And that means by switching off, the official technical term is post-stimulus voiding. And you can imagine if you repeat that, you have a kind of staccato peeing there, which can be used to artificially empty the urinary bladder in spinal cord injured patients. But we have to play some tricks in many cases with that stimulation to overcome that. That is the reason why some persons said we go in the spinal cord and try it out. We go into the brain and try it out to overcome this synergy in the peripheral nervous system. But I ask for your patience. This is one point where it comes to selectivity. How can we overcome that? Well, I'd like to go more in detail into that. But before we are there, and I had to play some tricks, what comes first, chicken or egg here, to give you an idea how this happens, and then we have to jump back from time to time to get into the details. What we need is an idea beyond that distance thing. So we have so far the electrode, we have learned it's about the nerve fiber diameter and it's the distance that is there. The third thing that is of importance is the electrical field. And this is something I think that depends a little bit on education. I had a colleague from mechanical engineering. He looked on differential equations and could tell me which part of the device would lift up from the table. That was completely awesome for me. I've had no idea when I look on differential equations how things move. I come from electrical engineering. I look on things and can tell you how the electrical field looks like. So I think everybody needs a certain approach to go there. What we should keep in mind, and this is not fully correctly drawn on that figure here, is that field lines are always orthogonal to metallic surfaces. So if we have metal electrodes, we have to imagine that the field lines leave orthogonally, then go somehow through the volume, and they end up orthogonally. And the further something is apart, the larger the field distribution could be. If we have things closely together, it's highly probable that the field is concentrated of that and gets sparser in further distance. So density of field lines gives us the strength. Strength is difficult here with two field lines. But I think we can agree that they are closer at the electrodes than they are in a further distance. What we definitely need to elicit an action potential here is a gradient or a change in the electrical potential over the length of an axon. So we have here two nodes of Ranvier. They have a certain distance, L, and we should have here a difference in the electrical potential. If we don't have any difference in electrical potential, we cannot excite the nerve electrically. So that means if we would place the electrodes left and right to that axon, we probably don't get much of an excitation. If we put them along the axis of the nerve, we get a good excitation. Here, both sides are the same, and that's shown here. This has been stolen, all the figures from a textbook on surface electrical stimulation, so the electrodes are all on the skin. Therefore, we always have here the skin as one line, then skin thickness, muscles, whatever is in there, and then the nerve and the nerve fiber. And as we see here, the field lines are more distributed in deeper layers. That means it gets more and more difficult to stimulate deeper nerve fibers if you are at a long distance from them. That's probably what you can take. Bone, fatty tissue are of high impedance, of high electrical resistivity, and they attenuate the electrical field. The same is true for scarring tissue. Whenever we have scars around an electrode, that increases the resistance, so like an insulator. We can play some tricks with the size of the electrode. And I always try to imagine such a stimulation that I start, for example, with an imaginary number of field lines. If it helps you, can say, well, let's start with 10 field lines for that kind of stimulation, and then you have a small electrode and a large electrode. And if you equally distribute those field lines over the surface of the electrodes, you see that the field line density on the smaller electrode is higher than on the larger electrode. And if it helps, you can transfer that to charge. If we would deliver current, let's say 100 charge particles, then they sit closer together at a smaller electrode than they sit on a larger electrode. And therefore, we quite often use charge density or current density. That's the current per area that we use. And by that, we better know how dense that all is. So in these cases, the active electrode should be the smaller one. and the field lines are more dense, and therefore we might get excitation there. At the same threshold, if we switch it off, the density over the anode, the larger electrodes, is less. The field density, charge density, current density is less, and therefore we probably, if we do it properly, we don't get that anodic break excitation because the threshold is not reached. Good. So, but what does happen if we put a piece of metal in something wet? And something wet could be either on the surface of the skin, because if we wait for a little bit, we either sweat or we know afterwards, after learning all the electrochemistry, we should take an electrode, gel in between. So it's wet, period. So, or we put it inside the human body, then it's already wet in there. Yeah? So we have the metal and we have an electrolyte. And what happens at the interface? This wet, no matter if it's inside the body or in the gel, is water. Do I have it here? Yeah, I have it here. So I jump now back and forth. Water is H2O. Yeah? We have two hydrogen atoms at an angle at 105 degrees and an oxygen atom. So the oxygen is more negative than the hydrogen, and therefore we can draw a circle and say this is an electrical dipole. So if we jump back, you see all those circles here. These are water dipoles. That's called the inner Helmholtz double layer. So Helmholtz discovered that, therefore this layer is named according to him. And then we have in water not only full water, H2O, but it's also dissociated to H plus and OH minus. And if we have an H plus, other water ions can, according to their dipole character, orient around that. That's shown here. And if we draw a line through that, we get the outer Helmholtz plane. That's shown also on the next slide. And if we apply an electrical field, we might either attract those charge carriers or those hydrated protons, or we can push them away due to the electric field. Charge of the same sign is repelled, opposite charges attract each other. And if we slightly change the field by slightly changing the voltage, these charge carriers travel a bit left and right. If we draw an imaginary line somewhere here, and we apply a charge, and this charge would go over that over time. Charge over time is electrical current. That's a kind of displacement current with equations that one uses from capacitors. Since we take our metal electrode as one plate of a capacitor and that imaginary line of the outer Helmholtz plane as the second plate of the capacitor, and when charge carriers wiggle and waggle left and right, we call that displacement current, and therefore we can deliver charge over time to the tissue that is, let's say, right of this picture here. The second piece or second mechanism that we could do is to put a really huge voltage on there and drive a lot of current over that and bring charge carriers to move from the metal into the electrolyte. That is called corrosion. So the electrode would go away. And we come to those mechanisms shortly in some minutes. The third thing is something that you might not have experienced yet. This is using metals that are happy to bind some species from the electrolyte, and they work as a kind of bookkeeper. Though they exactly count how many charged particles they keep. So one thing is, for example, a platinum hydrogen complex. Depending on the charge, this hydrogen is either dissolved, so we just have platinum, or it's attracted, then we have PTH. And since the hydrogen goes away as H+, we have a charge particle that we can deliver. The question is this always reversible? If things would be reversible, then everything would be nice. I could spend something, I could gain something, and at the end it's zero. If we look a bit more carefully on water, oxygen and hydrogen, we can imagine that we split it up and then we get oxygen gas and hydrogen gas. And if you get gas, it's hard to convince the gas to stay where it should stay. It diffuses away. And if it diffuses away, we cannot reverse that because the partners are no longer there for the reactions. And this is something where we have to deal with. Yes, please. Mm-hmm. That is a good question. Do we have an acidic milieu there if all the hydrogen atoms are attracted to the surface? The answer is it could be. So if we are in an equilibrium state, we have a pH of 7. That means there is a certain number. pH is the negative decadic logarithm of the concentration of hydrogen ions. So we have a certain number of hydrogen already there to get that pH 7. And then we have that shielding of the water molecules around that H+. So it's not that serious. That doesn't change that, and it only moves in space. So we do not generate more hydrogen ions. We just move them a little bit around. In this case, the pH stays the same. If we go to the third line here, and we would deliver all the hydrogen atoms at once and quite often and would not bind them back, then we get indeed a pH shift. And this is one of the risks that we have during electrical stimulation, that we get pH shifts. If we now link that, because of your question, to physiology, we can see in the brain, for example, if we do not reverse the potential that we apply and we release those atoms in a monophasic phase, not having the counterpulse for a biphasic pulse, then we can, for example, see that there is a collapse of blood vessels due to that change in the pH value. And if you have a collapse of blood vessels, your target tissue is no longer supplied with a sufficient amount of oxygen. So we can avoid that problem, not all the problems, but part of that problem, for example, by alternating currents. If we have biphasic pulses, first minus, afterwards plus, we don't run into that problem. And that is one of the challenges, that so many things come together here. If you solve one problem, you always have to see, oh, and I solve that, does that cause probably other problems, and where do I have the trade-off between those things? So here for you, just to read it afterwards, that's a kind of the spoken word now written down in slides, is the capacitive mechanism first, then the faradic one, and then the quasi-faradic, where we have that bookkeeper mentality on 3 different slides. If we just have the Helmholtz double layer, we have about 20 microcoulombs per square centimeter charge injection density. That means at an ideally flat surface, if you would count the amount of charge that sits there and wiggles a bit back and forth, that displacement current would result in that number. If you have a rough surface, you get more. If the roughness is such that you could, let's say, iron it with an iron board and you get a larger electrode, then you could deliver more charge, since the effective, electrochemically effective surface is larger. And this is a bit hard to read that in literature, because some persons go on the geometric surface, some persons calculate the electrochemical active surface, Some persons say, oh, I only use polished electrodes to overcome that question. So it's really good to read information in detail to come to that point. If you think this is too boring for you, you want to learn more, I can point you to the Guy-Chapman-Stern model that has many more differential equations to describe processes more in detail. You should know that this model exists by the names, but I don't ask you to go into detail there with that model. That goes beyond this course. But it's good if you see something that you know, okay, this is just the extended model of the Helmholtz double layer, where you can consider more effects depending on different concentration of the electrolyte. In the human body, we always expect that we have a certain concentration, and for that concentration, this model is good enough, the simple one. The Helmholtz double layer in detail, you have that charge, that's all what I already said, but here more in detail to look it up. If you have a charge, you can imagine that you have a parallel plate capacitor with two plates, one at the Helmholtz layer, one on the electrode. And if you have the charge, you can come to the electrical field. From the electrical field, you come to the voltage that you have over that. And by that, we know that we have a voltage drop across the phase boundary. That is one reason for that. If we go into corrosion, something we don't want to have, but we should know about that. It's irreversible, that means no stationary. You can reverse it, the polarity of the pulse, but it doesn't help because the kinetics is different of the reactions in one direction and the other. That means you have to prevent to overdo your electrical stimulation and to always stay in the limits that do not cause that irreversible Faradic reaction. And what do we have? We have water. We can water split up into oxygen and hydrogen, and if we do that, we get gas and it goes away. By doing that, we get some electrons. And what do we do with the electrons? Well, first of all, if we really overdo it, we can also split up chlorine. But then you really do something wrong. You can do that if you take a 9-volt block battery, 2 wires, a water of glass, drinking glass, and a spoon of salt, and you put the wires in, then it smells like swimming pool. Then you get gas bubbles, and 9 volt are good enough to also create chlorine gas. So we shouldn't do that in the body. The nasty thing that we get in corrosion if we use platinum as one of the electrode materials for implantable electrodes, we can get platinum tetrachloride, and if we have those biphasic charge, it's a tricky process because that process goes a little bit back and well, it doesn't go back and forth, but we get platinum tetrachloride, and that settles down on the electrode surface and creates, because it's like dust particles, creates a rougher surface. And by creating a rougher surface, you would increase that capacitive Helmholtz processes. And by that, it somehow, it's a kind of, it hides a little bit, and it's a kind of stealth process where you don't see that something is going on. There are measurement methods where you can do that, but not at that stage here. And then we have reversible Faradic reactions. That's the third line of defense in that first picture, where we have complex bindings on the surface, PTH, PTO, and this goes back and forth without destroying the electrode. Hidden in here is already iridium, but I like to comment on that later on when we come to more sophisticated materials. When we model that, those processes that we have, we can model that charging and decharging over the Helmholtz layer as a capacitor. And all those corrosion processes or non-corrosion things can be modeled as a faradic resistance in parallel. And as we've seen in the first picture, there's the interface layer and then comes electrolyte. And there's somewhere the nerve. And that part of the electrolyte can be modeled as a resistance in series, and you either find it in literature as RL, and then L stands for lead, or you find it as RA, and A stands for axis. If we take fundamentals of electrical engineering, then we can model that. We see, well, those who know see that this is a high pass behavior. That means at high frequencies, the capacitor is like a shortcut, and then we have only the excess resistance. At very low frequencies, the capacitor acts like an open circuit, so it's no longer there, and we should consider RF plus RL. And in the middle, it's a decline, a linear one, if we have a double logarithmic display in the Bode diagram. And if we make the equivalent circuit, we have the equation here, where the J is the imaginary number, so the square root of -1. Are you all familiar with complex numbers? Yeah? Okay. You don't have to like them, but if you have heard something about that, that's fine. And omega is here 2 times pi times f. So we get a cutoff frequency. That means the frequency where decay from the capacitive area is in transition to the constant area of the excess resistance, and exactly that transition gives us a hint where it is. That's the cutoff frequency here, Fg. You find it, G comes from German Grenzfrequenz, so you either find it with Fg or CO for cutoff, or it's mainly defined in the textbooks than in the text what the index means. Now my promise to be more complex. There are some materials on Earth that have funny properties, and what is beneficial in electrical stimulation is, for example, iridium oxide. That is called a valence change material. Depending on the electrical potential that the iridium sees, it's either 3 times positive or 4 times positive. And that changes over the potential. And this is what those equations say. So we see here it's either n or n plus 1. So depending on the potential, that material changes its positivity, and thereby it can bind more or less hydrogen or hydroxide. And by that, just by changing the potential, you get more charge. That's beautiful. With that, we come from 20 microcoulombs per square centimeter from the Helmholtz layer up to 2 millicoulombs per square centimeter, which is a factor of 100. So that's really cool. Same size, 100 times more charge without getting into troubles. If you do that modeling, you find that interface mechanism. So Helmholtz capacitance, faradic resistance is still valid, but you have in series to that an additional circuitry of those valence change processes, and then at the end again the electrolyte. If we want to bring that together, and this is more for something to look up, not to learn it completely by heart, then we see a kind of electrochemical potential series where processes happens. And electrochemists decided that the ground potential is the hydrogen potential. So hydrogen is at 0. That means we have to look what we have water. So we are in between hydrogen and oxygen. We want to prevent that. We look here through, oxygen evolution is at 1.2 volts versus RHE. That's the reversible hydrogen electrode, written down on the bottom line here. Very important because these abbreviations give us a hint where we have set the ground potential. Reversible hydrogen electrode is something we don't use in my lab because we would need hydrogen and we have to take a piece of platinum and flood the hydrogen around the platinum, and then you get the zero potential. That it's quite messy for our measurements. Therefore, we use other electrodes which also generate a stable kind of ground potential. For example, silver chloride. Since we are all too lazy to calculate silver chloride versus RHE, we measure what we measure and then say versus silver chloride. That's important to know. You always have to look what is the reference against which the whole stuff have been measured. And the rest happens in here and is important but not key now of my words today. Yeah.
But then the water window usually is from like creating hydrogen gas and creating oxygen.
Mm-hmm.
Right? And when this is with the reference of hydrogen, then you have the water window from, I don't know, 0 to...
Right. If we take silver chloride, which is 300 something millivolts somewhere, we have, this is here, it depends a little bit on the metal we are using. That gives a kind of open circuit potential, and so using platinum or iridium, we are from minus 0.6 to plus 0.8, for example.
So you just know when you use silver chloride.
Yeah, you know that versus silver chloride. Yeah, so there are other tables when say versus silver chloride you're here, and I show you a measurement method how to find that out. So the first thing when you do developments is to find out where's my water window with that material. Either you know that material on the water window, or you have a new material, then you measure that out, and then you take whatever, 20% or something like this to stay away from the limits, and then you define that as your working range. So some numbers here that you should learn by heart to have kind of landmarks or claims if you are somewhere around to know what is something. And this important if you are somewhere and people ask you, can I increase the amplitude by a factor of 10? Then you should know those numbers by heart to get an idea, are we still safe or are we creating bubbles here when using those amplitudes? We have different definitions, and I'll promise you when I have the Ilias page ready, you get that paper with all the definitions there. I'm really proud we were able to launch a Nature Protocols paper where all this known knowledge is now summarized together. Don't say that we all invented that, but we were the lucky ones who were the first ones who submitted that. Impedance, so it's the resistance over alternating current, which we use. We have charge delivery capacity and charge injection capacity. And this is something that comes on detail later. For us, the important thing is the charge injection capacity. If I have a rectangular stimulation pulse, how fast, which is fast on the edges, how much charge can I deliver? The middle thing here, the charge delivery capacity, is an electrochemical measure under equilibrium processes. And that would mean I'm very slow in changing the voltage such that every process that like to happen has enough time to happen. Yeah? If I have a step response, I'm very fast and probably the slow processes cannot happen because it's already over. Yeah? And therefore the charge injection capacity is always smaller than the charge delivery capacity because it goes under faster boundary conditions. Just as a repetition for those of you who are probably not that familiar with all those details, electrode impedance is mainly plotted on the Bode diagram. Which is the magnitude of the impedance and the phase of the impedance. And it's double logarithmic. So this is a log scale. You don't see it here in that graph because this is already here the magnification in decibel, and the decibel is a unit that is already logarithmic. So therefore we have no logarithmic scales here in that display, but the y-axis is logarithmic and the x-axis is also logarithmic. And in that case we see here a decay and we see here a decay. And if we would go further to the right, we would probably see that this goes into a constant value. With that, decay, cutoff frequency, another decay, I would say this is here. Could be something like that. You're not supposed to know that. I just want to complement here that. And we can draw also information out of the phase. This is a complex value, the impedance. So we use for the impedance a sine wave that we apply and measure the outcome. The outcome, if we do it correctly, is still a sine wave, but may be phase shifted and attenuated in magnitude. And we need then either the magnitude and the phase to get the full information. This is done by the length and the phase angle. Or we can say, well, if we put that into the imaginary plane, we get the real part of that and the imaginary part of that. And that is equivalent. Real part and imaginary part, if they come together, this is called the Nyquist diagram. But it's equivalent. In some cases, it's better to use the Bode plot. In some cases, people are more happy with a Nyquist plot. If you have the data, you can transfer them by those two equations here, or those four that we have here back and forth without loss of information. The question is how we should measure. And I have to. Yeah, just a minute. I did something here, having too thick fingers. Now I'm ready for your question. Yeah. Right. You lose the information of the frequency. Is this then actually useful? That is an excellent question. It depends what you want to see. If we want to see what is the impedance over frequency, then we need the frequency. For example, to match an amplifier to the electrode. Yeah? Matching means there that we have the conjugated complex impedance as input of the amplifier as the impedance of the electrode is. then we have the best power transformation in between. Then you would need the Bode plot of that, because you want to see where it goes. There are other questions, for example, if somebody asks you, or would ask me, if we go to low frequencies, do you think this is infinite diffusion, or do we have some diffusion limitation due to surface roughness? I could look on the Bode plot and don't see anything. If I would look on the Nyquist plot, and I try to just probably... So I hope it works. If I would have the Nyquist plot, please forgive me, that should all be straight lines, right? Yeah. So this is a real part of that. And this is not a trick, since people always want to have something on the upper right-hand side of the page. We use the negative imaginary part going upwards. That is completely stupid, but that's convention. Yeah, so we have minus imaginary part of z on the y-axis. Yeah, we have a capacitance, and if we have a capacitance, the imaginary part is always negative. And we know from those electrodes that there is nothing like an inductive mechanism. If we would have an inductive mechanism from a coil, Z is J omega L, then this would be positive. 1 over, I'll write it here, one said Z is 1 over J omega C. And that means having J in the denominator, right, is minus J over omega C. So whatever we do, this is negative. And we have no mechanisms that react inductively. Therefore, we don't get in the upper right corner. And that was the reason why people said, oh, come on, let's do it that way. And you get, if you have a C and an R, or two R's and a C, you get something like that. That is here, for example, RF plus RL, and this would be RL. Yeah, you have only the real part, and then in the middle, I should know that by heart, but I don't know that. There's here that maximum that you can derive where you get an idea about C. But you're right, you never know where it is. You know from the equivalent circuit, sorry, I'm losing here the language. We assume we would have something like that. Or other way around, there are right. If we are at omega equal to 0, we have an open circuit. Yeah, open circuit is RL plus RF in theory. And if we go to omega to infinity, we have a short circuit here. That's what I want to do here. RL, RF. Short circuit, that means RF is bridged. That means we know we are running in that direction. Please forgive me if we go omega towards infinity. And then it's not, we can assume that if we go to 0, we have RL plus RF, but in reality, due to the surface roughness and the thing that this is not the real model, but an approximation, we have something that goes up here. That's due to limitation of diffusion. If you're very slow, I imagine it that way, that there is, for example, an hydrated proton and another atom comes and cannot go across. Yeah, and by that, you stop somehow the processes a little bit. And this is called diffusion inhibition. That could happen, for example, if you have very long, deep pores where something is in, let's say a water molecule, and due to the driving voltage, it should go out, but it cannot because the pore is too deep. Yeah, so it's not there to contribute in other processes. And then you find out if this is really a straight line or if this is a curved line, and by that you can go to fundamental chemistry textbooks and find out what mechanisms happen at the surface.
This diagrams really show you this.
Yeah, yeah.
Okay, and the moment you can't.
And this gives you, sometimes the Nyquist diagrams give you then information that is easier to get visually than from the Bode plot. But this goes really, you know, I cannot measure that because I don't have a Faraday cage and a measurement equipment that is so expensive to do so. But if you're really Jochen Kieninger, for example, as the godfather of electrochemistry here on campus, he has that stuff around and he could really go into that increasing line. Not with every electrode, but with some. And this is the reason why you then switch to that, to really see that and to find out what happens. Also, if you do real electrochemistry, when it goes on reactions on the surface where some partners react and you want to see charge transfer or something like that, then you really go into those details. So, to completely confuse you at the end of the course, I want to go now on the last slide, and this is something I repeat next time, that we back that up and don't lose it. Let's see if it works like that. We go to the measurement equipment. You might know that if you have done an electrophysiology course or cell culture course with electrically active cells, or if you have done an engineering course in electrical engineering, measurement, instrumentation, if you measure something, you need the ground point. And you always assume if a current flows, that this does not influence your measurement. That's unfortunately wrong in electrochemistry. If a current flows, this current flow could influence somehow your measurement. I mean, you want to measure the current, but you don't want to change the potential that you apply by measuring the current. And sometimes you always want to know where your potential is. And if you remember that slide with the different mechanisms at different electrochemical potentials, probably you want to change your potential to see what reactions you find at that potential. Given that you keep that potential constant, then you change slowly a so-called small signal around that potential that you have. And these tasks are performed with something that is called a potentiostat. A potentiostat is a measurement setup where you need, first of all, 3 electrodes. The electrode that we like to characterize is the working electrode. Then we need to have a connection to our bath in which we measure where we know what potential that is. And we take a silver chloride electrode as reference because that electrode is always staying stable no matter what happens. And we have a 3rd electrode which helps us to deliver whatever we need in the electrolyte. That's called the counter electrode. The counter electrode is in most cases made out of a relatively large piece of platinum. And then we have the first operational amplifier where we apply our input voltage. And you see here we have a ground. That's the electrical ground. And this could be, for example, the sine wave for recording the impedance of the electrode. In our case, being simple, this is, for example, 50 millivolts sine wave. But we could also have here so we could have that sine wave, let's say the 50 millivolts or 10 millivolts, but we could also add a DC potential if you want to shift that. But that gets very complex then. With that, if we take, we get on the positive input terminal of the operational amplifier. In theory, the negative terminal follows the positive terminal. That means the potential we apply here goes in the silver-silver chloride electrode, giving us up and down what we want to have. The platinum counter electrode is connected to the input terminal versus the salt water bath as a feedback loop. And this is shown on the right-hand side. If we have the first operational amplifier, we have the plus and we have the minus, and the minus is fed back over the reference and counter electrode to the output terminal. The salt water works as a resistor, and the electrolyte E and the working electrode are shown here, and this goes then over an amplifier. And if we look here, we apply a potential, and what we measure here is a current. Then we use a current to voltage transverter here to get back a potential, since a potential is better to put into the next stage of whatever measurement equipment, but we are lazy persons. We need to have the inverted thing here, the inverted input terminal. That means we must multiply it by a factor of -1 in mind, and that never works. Yeah, sometimes you forget your -1 multiplication, and therefore we have a second inverter here that makes minus times minus is plus again, and we have 100 kilo ohms over 100 kilo ohms. That's a magnification of 1. That means it just turns the -1 to +1, and we have then the output current that flows here. That means by having 1 kilo ohm, so our phi out, European experts already see that I stole this graph from a Dutch publication with the out. That's Dutch for out. That means our output potential is the resistance that we have here, 1 kilo ohm, times the measured current, and then we can divide the output voltage by a kilo ohm and get the measured current. And by that we have then the current, input voltage, output current. We can divide that, see the phase shift, see the amplitude, and get the complex impedance by that. If you buy something, if you make something like that by your own, you're about 30 euros with the components. If you take high-end amplifiers, you see here 3 operational amplifiers. You get chips with 4 in them, then it's 1 for free. Or you can buy a device with multiple channels with a lot of compensation of temperature, of artifacts, of interferences, and then you are in between 10 and 100,000 euros. But it's worth doing so, because if you do it by hand, it's a nightmare to get things out. That's good if you just want to learn how that works, but it's better to buy a commercial one then to see if it really goes. And this will be our workhorse. Also for the question, where's my water window? That comes next week then, and but this is for the impedance. One thing that I said, and might probably not be in your fully attention, therefore I want to have it repeated here. The input input voltage should be in between 10 and 100 millivolts. Should be very, very small. Otherwise, you are in voltage ranges where you might induce already some reactions that you don't want to monitor. You want to monitor what is the material as such, right? If you would be, let's say, with silver chloride, you would apply 1 volt, then you could be already in both sides plus 1 volt, minus 1 volt is 2 volts. The water window is around 1.2, 1.4. You could be already exceeding the water window with characterizing your electrode. That will mean you destroy your measurement object by identifying it. And this is something you shouldn't do. Therefore, very important, take those small voltages. I mean 10 millivolts at an electrode impedance of a mega ohm is not very pleasant with respect to the current that you expect. Yeah, you are at very tiny currents there that you expect, and that's sometimes the challenge, that you need shielding, that your laboratory lamp is not overtaking the measurement instead of your device under test. But that's life. So that's the reason why those measurement devices are so expensive, that already, let's say, cable influence is compensated, or you can calibrate the whole setup, including the front end electrodes, before you go into measurements. And you have then clever software in the background. I'd shown you the Bode plot and the Nyquist plot, and drew equivalent circuit next to it. Sometimes you have no clue what this is. And then there comes software with that gives you a first hint. What kind of equivalent circuit could you have? Or you have an idea what it could be, and then it does some fit for you, and giving the numbers you can have a look if this makes sense for you, or if you should adapt your model then later on that. Yeah, good. With that, we are at the end for today. You should, if you look through those slides later on, you should look with those eyes to ask yourself, how does why are electrodes efficient in electrical stimulation? So what does the field do if I extend the distance between the electrodes, or if I have a larger distance to the nerve? What typical pulse shapes do I have? And that's the hard part then, what typical electrochemical processes occur at the phase boundary? That's the core of today's lecture. Next time, I'd like to go with you into some typical measurements. So we have already here the electrode impedance. I want to go into charge delivery capacity and charge injection capacity, that you get an idea, what does this measurement do? And can I do that if I'm in vivo? That's a second point, and I don't spoiler the answer with that. So there are options how we can do in vivo measurements if we know some boundary conditions. That's the job for next week. So far, thank you very much. You survived the first part of the electrochemistry. Happy to have you here, and looking forward to seeing you again next week again. Thank you very much.